7.2. So last time we saw a special formula for the area of a circle, which is pi multiplied by r squared. And if you have a volume, then you take that area and multiply it by delta x, by thickness of that circle, so it becomes a disk. So if it's thicker, the delta x is bigger. And that's the idea. And then we also did the integration on this. In the case if you don't have a disk, but some surface that is not really a disk, but some curvy portion of it that was sliced with those delta x pieces, so we would turn this into function f of x instead of radius, because radius will vary at every point, so that would be a square of that radius. And of course, delta x always turns into dx when you take the limit, and pi you can take outside of the integral. So it is the same thing, and we have variable ready, and that's why it's dx, because we take a limit, so it's very, very small. So let's do an exercise. Let's do the setting so we start to feel a little bit more comfortable about this. So let me try some exercise, let's say 4 to start, and then we'll see what else will be added to this story. So 4 should be pretty straightforward because it has a square root, and that's why I'm starting with it. So if you want to find the volume, and the point of story is that you are rotating about x-axis. This picture is not what we're actually trying to find. The picture we produce if you add a little bit more stuff here, and if you start to rotate about the x-axis, right? And that will be looks like a half of a ball, right? So if you imagine yourself this figure, it looks like it's like a ball with a cat in the half. So if you know the formula for the volume of that ball, you could probably not use integration, but let's say we still use it. So the formula here says multiply by pi, our integral, and then our function that gives us radius r. So just to be more clear, we have a radius of rotation. Since we rotate about x-axis, that will be r, which is the same thing as our function at every point. I select in between 0 and 3, so we start at 0 and we end at 3. That's how my integration will be defined. Right? And then, so at any point between 0 and 3, we have a radius, which is a function given as a square root, whatever, 9 minus x squared, okay? And this needs to be squared. This radius has to be raised to the power 2. And then dx will be attached to it. And then I can just integrate, and it's x to the power 2. So we need to integrate 9 minus x squared, right? Because square root and square will cancel. And looks like we're in the first quadrant, so everything is nice and positive, and that's but it's very good. And yes, we'll later gonna rotate about various other things, so we'll need to do a little bit of adjustment. And that's why I think it's very important to understand the whole picture, because when you get it, it's, I guess, doable for all the exercise. So 9x we have here, right? Antiderivative of 9 is 9x because derivative of 9x is 9. And for formula of antiderivative of x squared is x to the power of 2 plus 1 over that same exact power, which is 3, right? And then we put the upper and lower limits in fundamental theorem of calculus. So we go with 9x subtract 3 cubed over 3. And that's great, they nicely cancel. And also when I plug in lower limit, let me plug it in. So the 0, now I plug in, it all becomes 0, right? So that's why I like 0 so much, because it's really nice to have 0 because it disappears. So what do we have here? 3 squared is 9. Oh, I had to put not 9x, but 9. I need to multiply it by 3, right? So clear this. So I need to wake up, I guess. So we now plug in 9 times 3. And looks like this will cancel and give us just 9. And 9 times 3 minus 9 times 1. So it'll be 9 times 2 or 18. So we've got the nice answer, but don't forget there is pi there. It's still be multiplied by pi. Something like that. Okay. If I remember it right, the formula for the volume is something like pi r cube over 4 or something. It's not very widely utilized for volume of ball, but you just can check it out. It's half of ball, so it's r cube is gonna be, looks like pi r cube, right? Volume of ball is pi r cube. So if you get r cube, that's 3 cube 27, but it's half of ball, so it's 18. So you could have guessed the answer right away. And I think this is important to realize that guessing is good, because sometimes some students might be taking so-called graduate record exam, GRE, if you plan to get a degree higher than bachelor's, and if you're applying for graduate school. And graduate record exam might have something related to finding volumes, very popular. And you don't need to waste time on the graduate record exam doing all this antiderivative pain, but just use the formula for the area, for the volume, sorry, for the volume, not the area, volume of the ball, which is pi times r cubed. And if you see the half of the ball, then it will be half. So if r is 3, then it's right away give you the answer, so that you don't have to do anything but give the answer right away. And the importance of that is in succeeding in that type of exam, because if you get stuck with this exercise, you're not going to have enough time for the other exercises. So the point of story is you want to, well, make sure you utilize the time quickly. And that's because they give you like 3 hours, I believe. And if you try to do all the exercises the way you're doing it in class, it might take a time much longer than 3 hours. So some problems you may even want to skip if they too time consuming, because the practice shows nobody does more than half of this exam. So it's just, if it's too time consuming, even if you can do the problem you don't want to get stuck with it, you can skip it. So you do things like this one shorter way. And this is, I think, important. But anyways, I say, Alex, so I can do it like that also. Yeah, sure. I don't mind. As long as you show work, and if you show work means you write the formula, then they'll of course accept this as a perfect work if you found a shortcut. But of course, if they say set up and evaluate the integral, so they say set up and use the integral, not some other approach, that's how they expect you to do it. Well, anyways, so that's what we learned to do last time. So it could be the exercise with one solid, or it could be exercise with two solids. I think it's a good idea for me to do exercise like 5, because actually it's going to be, maybe just show you on the picture. So they have awesome pictures here. So nowadays they have various figures like the one they have here. They produce a revolution of not just one curve above, but there is a curve below. So they actually want you to get that cone and take it out. So that cone needs to be subtracted, cut out from that like semicircle, which is probably like a half of paraboloid, parabola-like figure. And they want you to subtract, drill something out from it. So that way you will be subtracting a portion, and that's something analogous to what we did in the previous section where we had upper and lower curves of integration. So let me do the exercise here with the problem 7. I think can be a good picture. Actually, not 7, but 5. 5. Just want to clean a little bit here. So they again rotated about x-axis, and that's what they nicely put in the picture for us, and that's great. So what you're gonna get is rotation about x-axis. See, that's why it's a good idea to first of all realize what they're talking about. So there'll be a figure looks like bounded by 1, so it's going to be exactly the cone structure. Like a cone, and then inside of the cone, maybe I'll make it bigger. Inside of that cone, they drill out a piece. So from inside of that cone, they use the function down below the parabola. So what they're gonna do is take out a part of this cone. So something like that. See, they take another cone out, but the cone with a curve inside. So technically you could find the volume of cone on the outside, but there is no way you'll be able to find it on the inside because it's given to you. Actually, the other one, the first one, is also with parabolas, so they both are not very nice for intuitive calculation, right? So, and that's why I need to subtract the volumes or subtract those ready. So I need to add any point of x that varies from 0 to 1. So I already know how to start my integration. So I have x that varies from 0 to 1, which means my variable of integration is going to be x, so it's dx. And then I need to subtract from the volume of the one out on the outside, and the cone, the big one on the outside, will be the one with the radius, let's say capital R. For the big one, I'll use big R. And the one on the outside is going to be the lower power of x squared, right? Why is it x squared, not x to the power of 5? Well, it is important to realize, oh, there you have a picture. So that if you have a parabola x squared, on the interval from 0 to 1, it gives you smaller values than values of y, than fifth power. So they intersect each other at 1, and then at 0.11, and then the x to the fifth, of course, starts to increase faster than x squared, but x squared is above an interval from 0 to 1. So the one that is on the outside will be x squared. So that'll be like my capital R, which also needs to be squared because it's R squared, right? So that's envelope, capital R squared. And whatever it is, we just squared. And then the inside portion, this is going to be a little r. And little r is x to the power of 5, right? And that one we subtract, so that will be minus a little r squared, and that will be squaring x to the power of 5. So once again, I don't care what the functions they give us. I just want to make sure the upper one minus lower one. And that's the analogous idea to areas as we find the volumes. And of course, it's pi radian on the outside. And again, this is a nice antiderivative. It looks like we're going to deal with tens power of x subtracted from the fourth power of x, right? So you need to find antiderivative of x to the fourth, which is x 4 plus 1, 5 over 5, and for the tens power, I add 1, get 11, and of course, same is in my denominator, and it's from 0 to 1. Again, 0 is nice, and of course, it's not going to be everything that nice. But once again, our goal is to get main idea of setting up the whole thing correctly. And if you end up getting some not nice numbers, then, well, you may spend a few days on your own messing with all these not very nice numbers. But here's nice. So when I plug in 1, we have numerators both equal to 1. And then when I substitute 0, everything becomes 0. So from 1/5, I subtract 1/11, whatever it is going to be, is 6, 1, 5. And I'm sure you know you have your own ways of doing arithmetic, but 11 minus 5 is going to be 6 over 55. And then pi attached to it. And that's our volume. So people say that's cubic units because it's volume. So it is in little cubes, right? Because it's volume. That's good to realize, by the way. I'm sure you know that. So anyways, these are the nice cases. And of course, not everything is that nice. And this happens when you start to rotate not about the x-axis, but about, let's say, some other horizontal line. So we'll start with horizontal rotations, and the exercises in the next group says, what if you rotate, let's say, about y is equal to 4. So if I wanna do one of these problems. Let me try one. For a change, maybe I can try 18 with secant. So let's get some trig exercise. So if I have a function secant, and if I rotate about y is equal to 4, remember the graph of secant 1 over cosine. So it's good to realize that secant 1 over cosine has to do with cosine function. Cosine function like that. And you can use calculator, graphing calculator shown to you. And now that's cosine function. And then you need to take its inverse. So you forgot how the graph of cosine looks like. So that's 0.pi, right? And then you take the inverse. So it starts at 0.1. And it goes to, here's pi over 2, because that's pi over 2 intersection. So we have something like that. That's a graph of arc cosine. So the point is, you don't need to remember so many graphs, but secant is cosine. It's already been a while. And I'm trying to graph arc secant, not arc sine, arc cosine. This is actually arc cosine. Sorry, I got carried away, but I think it's a good idea to refresh anyways. So I didn't graph secant, I graphed arc cosine from 1 to negative. So that's it. Well, we will utilize this eventually, but I guess I need to be a little bit more careful. So arc secant, secant, how to graph secant. I think it's not a bad idea that I refresh your memories on function cosine. So let me write secant or 1 over cosine, right? And I say, Alex, what are you doing? Well, I guess I'm enjoying it. So the point where the intersection happens, pi over 2, right? Pi over 2. We have asymptote because it's 1 over cosine. Remember, 1 over cosine. So when cosine is 0, we have it undefined, or we have a asymptote. And then how does it look like? Is it approaching upwards or it approaching downwards? Arc 1 over cosine. Well, looks like it is going positive, so it will be here and then down. So analogous to function tangent, but it is just analogous because it is bounded. It has vertical asymptotes. And then it repeats infinitely many times to the left and to the right. And that's why we care only about the first piece. That's what we're working with. It's good to realize that, and no wonder they give us the part to rotate that is from 0 to pi over 3. So pi over 2 will be the intersections. Let me write it like that. Here's pi over 3. And pi over 2 is that. We don't need pi over 2. So it looks like we take this particular piece, and then what we do is we rotate it not about, so what particular piece? We take this particular piece. See? That piece. And now we need to see how we rotate it. And we don't rotate it about x-axis. We rotated about y equals to 4. Do you see that? I see Alex enough. I see that. Okay, so y is equal to 4 is somewhere above. Right? So this is your axis of rotation. So when you start to rotate it, look at what happens. You're gonna get that point gives us that circle, and that point gives us a big circle. You see what's gonna happen? How about that? So this is gonna be the figure that we're trying to find the volume. So this green thing, of course, it is. Maybe I can make another picture. So otherwise it'd be too much mess. So that will be like a ring. And it will be hollow on its inside. But it's always a good idea to imagine, to actually try to draw what is that you are trying to find the volume. And say, how do you know, Alice, that this is hollow? Well, because it's cut, right? So it is being cut, and what we rotate is just the one here, right? So what do we produce as a figure, actually? Well, remember what we're rotating? Not this, but this will give us the solid. So this is going to be right here. So we cut out, let's see what we cut out. The, like that piece, like a pole, right? From the figure, and it's correctly above. Below is correct, above it was not correct. Fix it. So the one on the outside is the one right here. Yes. When you rotate this, x-axis gives you this piece. So what is that we're trying to find? That's the solid part, because that everything else is going to be, looks like opened. So this one is cut out as well as the green thing is cut out. So maybe I can try to finally give that ring. And there is a stuff, there's one. So if you look at it from that direction, it will be cut out, but it's not going to be a real ring. It'd be the ring with various measurement of the hole on the inside. You see, the hole on the inside is varying. So trying to get a better picture. So it's one. So if you look at the variant of your x, then the one on the inside, and there'll be another on the outside. So if you make a slice at various values of x, that will run from 0 to 2 pi, or to 2 pi over 3. So if you integrate from 0 to pi over 3, then you will be taking any value of x in between of 0 and pi over 3, and then you will have function on the outside and the function, the radius on the inside. And that's what we produce. And on the outside, it's nice because on the outside, it's always the same. It's given to us by y is equal to 4 here. Oh, sorry, not 4. It's going to be over there. It's 4 and 4 is 8, right? On the top. And on the bottom, it'd be x-axis, which is y is equal to 0. And then the function that we have cut out on the inside is given to us by our secant function, secant, or 1 over cosine. So how can I put this down then? Well, upper minus lower, but please notice that when you be taking the bigger radius, call it as capital R, that will be 4. Capital stays the same, it is 4. So once again, it's capital R squared minus little r squared. So capital R stays the same as 4, so it'd be squared. And the little r is a secant. I try to write it really slowly. I'm not sure if that was helpful. And then go dx, and then, of course, pi is in front. So technically upper minus lower, and that's pretty standard. And now, well, just do the antiderivative and get the answers. And I guess the ending is what you can do yourself, so you don't really need me, or I'm sure you know how to do the antiderivative. And the secant squared was the antiderivative of the secant squared. Is that the tangent according to the formulas? So please notice that if you go in front of the textbook in the beginning where the formulas are, you will see that antiderivative of secant squared is tangent. We saw this last time. In fact, you can always justify it by taking derivative of tangent, which is a function sine divided by cosine, and then use the quotient rule. Derivative of a quotient, you will be able to do a little bit of work with those derivatives and algebraically get secant. We did it last week, so if you forgot, I think it's always a good idea to refresh, but the point is that we will use this antiderivative here, so maybe I will continue on that side. So we end up with pi, and then 4, antiderivative of 4 is 4x, and then it's actually not 4, it's 4 squared. Okay, 4 squared, whatever, 16, minus the tangent, right? Secant squared, that's tangent. See tangent squared? No, it is just tangent. And then we go from 0 to pi over 3, and that's it. That's our volume. It's not too bad, even if you have a secant. So I decided to choose one of the trig functions just to make sure you feel comfortable with this. So that would be what? 4 times 4, 16. 16, and there's pi. I'll leave it on the outside. So you probably already did the antiderivative. Are you doing it? Try if you feel comfortable using this fundamental theorem of calculus. I'm sure you'll be able to do it faster than I. So pi over 3, upper limit pi over 3, I put instead of x. And what's the tangent of pi over 3? Well, I need to use the line of tangents. I guess the fastest way is to use line of tangents. And then again, 16, I need to multiply it by, now it's 0, right? and subtract tangent of 0. Well, tangent of 0 is 0, so looks like, again, my favorite term shown up. So how do you use a line of tangents? I think that's another thing to realize. So there are only two important values for tangents. So if you use unit circle, be able to attach the line with equation x equal to 1 to it. Then there are two important angles here. I didn't draw circle correctly. Line of tangent so you can see better. Here's better. So there are two values, one on the level of 1. So that's for 45 degrees angle, right? 45 degrees. And the other is for pi over 3. It's actually pi over 6. So that'll be tangent of angle pi over 6 or 30 degrees, right? Less than 45. And the other is tangent of pi over 3, which is more than 45 or 60 degrees. And please notice that tangent of 45 is 1, so this will be less than 1. It's 1 over square root of 3. And the other is more than 1, so it will be square root of 3. So there are numbers that I need to remember from, I guess, trigonometry class, such as 3 and 1 over square root of 3. So whenever you have more than 45 degrees, it's root of 3. So you end up with 16 times square root of 3. And then 3. And tangent of pi over 3, tangent of, sorry, this one just stays. It's tangent of pi over square root of 3. So we got the answer. It's 16 multiplied by pi over 3 times another pi. It's pi squared over 3. And whatever it is, just some number. And you can put in the calculator. And this one is pi distributed times square root of 3. So assumption. Not very nice number. Well, the function was not very nice either, right? So it was dealing with secant. So not surprising it is in that format. Again, please double check arithmetic if needed. You can always fix it. So rotating about not the axis, but some other lines. And that's interesting to think about. Next time we'll do another exercise like that. And now I want to show you some other interesting rotation, not about the horizontal, but about vertical line. Vertical line. So let me clean this mess, and I want to look at the picture that they provide. They provide always nice pictures, and that's the ones that I'm gonna utilize, because my pictures, of course, are not far away from what they generate using computers. So definitely kind of jealous, but trying to do better and better. So in the gradient with respect to y, not with respect to x. In other words, when you rotate it about y-axis, you definitely cannot integrate with respect to x. So what they're doing here is they do a different rotation. So if you take parabola and you rotate it about y-axis. So your y will vary, looks like here it is varying from 1 to 2, right? Something like that. So 1 to 2 for the parabola, so you can find the volume. But that volume you need to drill or cut out from the cylinder. So you're gonna have to probably have two integrals because there is no parabola below 0.1. So you're gonna have the integral from 1 to 2 that you will be cutting out, or you will be subtracting it from the cylinder. So if you try to look at the equation of parabola, which is y is equal to x squared plus 1, then you need to integrate y from 1 to 2 with respect to y, so you need to rewrite this as function of variable y. Your y is variable. So y is not a function of x, but x is function of y. So you need to bring 1 over to the other side and then extract the square root. And that's exactly what they did. So your little r is square root y minus 1. In other words, whenever you're going to integrate or rotate about y-axis or any other vertical line, then you need to integrate with respect to variable letter y. And that's the point of this change. So you can always pull out x, and then you use this little radius squared. So it will be a square root from y minus 1. And it's not that bad because it has to be squared. It's r squared, so square root will disappear and you will get something nice. Well, for themselves, they decided to use a nice exercise. And this is going to be subtracted from the volume of cylinder. And you can use the formula for volume of the cylinder if you want, or you can just integrate from 0 to 2 with respect to r, and radius capital R will be the same as 1, right? R is equal to 1. When you rotate again about y-axis, it is 1, so 1 squared dy, of course it's pi in front of this guy as well as in front of the other. Just like that. So we don't utilize parabola, we have the cylinder, so just reduce 1 everywhere. So we try to bring, oh, they say here capital R is 1. So bring down so you see the integral they produce here. So it's 1 for the first one, and the second is you're using R, which is 1 squared. When you say, Alex, why do they have 1 here? Why do they subtract it from 1? Well, because they looks like put it both in the same and 1. So why do they have 1? Subtract 1 squared. Well, let's check this out. So it's, if I, because I'm doing it differently. I'm doing it a little bit differently. They're trying to do with one formula, but I do it with 2 separate. But the answer has to be the same. So anyways, let's check it out. The answer has to be the same. I just want to show you that there, instead of from cylinder, so the one above we have cylinder, I think it's good that I do it differently so you will be able to see yourself. So cylinder, and the one that I subtract is that little cup, right? Like a cup, the one that we have up here. So if you cut out from the cylinder that little cup, you will get the result. But what they're doing is they split it in two integrals. So they cut this thing in half. So they do the cylinder not from 0 to 2, but from 0 to 1. But second piece, they cut out from the cylinder that cap, and they go upper minus lower. So that's why they have one minus the other. But it'll be the same thing at the end when they get the volume. So that's, I think, a nice thing to realize. I hope I will get the same thing. So it's going to be what? Y, right? Because we integrate with respect to y because it's 1, so it's y because derivative of y is 1. And then from 0 to 2, so that'd be my first value, and it'll be 2 pi, just 2 pi. So that's the volume of a cylinder with radius 1, 2 pi cubic units. And for the other one, when I have a square root, so it will be subtracting pi multiplied by, looks like, again, the structure will just give me antiderivative of y minus 1, right? Y minus 1. And I was getting a little bit too much. So it'd be a y squared over 2. And then we subtract just y. And again, we need limits of integration, but they will be 1 to 2. See, there are different limits of integration compared to the one way they do it. And then we now need to put those 2 and 1. So if I put 2 squared over 2, subtract 2, that's the upper limit. I'll use pi later. And minus, that's 1 squared over 2, subtract 1. And then pi is on the outside. Okay, so what do we have now in here? Well, it looks like it's 4 over 2 minus 2 is 0. And then we need to subtract. And that's 1/2 says negative, and negative is positive. So it'd be pi over, right, 2. So that's 4, just double checking. 4 and minus y, right? It's y squared over 2 minus 2. I just want to make sure I do it without a mistake. So this is 2 minus 2, that's 0. And then minus and minus would be plus. And then 1/2 minus 1 is going to be negative 1/2. So the volume of the lower one, the one that I subtract from 2 pi, is pi over 2. So when I take and subtract these two volumes, I'm going to end up, looks like, with 3 pi over 2. 2 pi subtract. So let's see what they can produce. It's interesting. 3 pi over 2 or not. Oh, yeah, I got lucky. 3 pi over 2. So I did the arithmetic correct. If it'd be not 3 pi over 2, I'd be in trouble. But I guess it's a good thing that you were able to see that you could do it various ways, right? The same exercise. I think that's really too much load for one day, right? So next time I will continue with this, and next time I plan to give you a little quiz. So I'm not gonna give you a problem, of course, like that on the quiz. What I think I will do, I will ask you if you integrate with respect to X or with respect to Y. So I'll give you the setting, and that way will be pretty straightforward. So you just guess either dx or dy. I was thinking about doing it today, but I think we need to put a little more time into this whole thing. So I'm gonna stop at this moment. So I'm gonna stop to record. If you have any questions, please, if you have any. If not, we can just log out and enjoy the rest of the day. Stop.